Okay, hello everyone, and welcome back to another R tutorial. Today I'm going to be continuing our statistical workflow on the chick weights data. If you remember, last time we looked at the chick weights data set and saw what it entailed, and we separated it out into two different feed types as opposed to all six, so that we could look at a small subset with two factors. We did some QQ plotting, we did a histogram with the normal distribution curve. We set our rules of engagement here with our alpha being 0.05 and our null hypothesis for the whole workflow. And then we ran our normality tests. And so I'm going to rerun all of this code. Now you could go up through here and just rerun each chunk individually. You could select all of it and hit Control Enter. That's our shortcut for running selections or lines. But what we can also do is click on this button here in the middle of the top right part of any chunk, and that will run all of the chunks above the chunk that you're in, except for the chunk that you're in. So it won't run this one, but it'll run all of these chunks. Or, alternatively, you can go up here to Run in this menu, go to the drop-down menu, and there's a whole bunch of options here, including at the very bottom this Run All, and that will run all of our chunks. So I'm just going to click Run All Chunks Above. It will pull up everything. It will give us all of these plots that we made, and then I'll just run this chunk on its own, and now we have our normality test results again. Now if you remember here, our normality tests came up quite a bit above alpha for most of them, all except for the chi-squared. And that means that based on the null hypothesis of these tests being that the data are normal, we can accept that, or at least fail to reject it, and thus we will conclude that the data is normally distributed. So the next thing to do after we found out whether or not the data are normally distributed, we want to test for the equivalence of variances. To do that, there are a couple different tests we can run. Like I said, in the beginning of this workflow, I'm not a statistician, so there are probably other ways to do this. There may be better tests out there. Not all tests are created equal, obviously. And so I'm just going to go with the two tests that I'm most familiar with and discuss what little I know about the differences between the two. So the two tests I'm most familiar with are Levene's test and Bartlett's test. And based on what I do know about these, Levene's test has a tendency to inflate type 1 error, that is, rejecting the null hypothesis when we should have accepted it. However, Bartlett's test is more sensitive to departures from a normal distribution, meaning if your p-values from your normality tests, such as these, are really close to alpha, let's say like 0.1, like if they are all as low as this chi-squared, then we might say that it's not super close to normal distribution, or it's not strongly normal, then you might want to avoid using Bartlett's test because it's a little more sensitive to that. So in this case, if you're choosing between the two, if the p-values of your normality test are exceptionally low but still above alpha, then you may just want to use Levene's test to be safe. Of course, Levene's test tends to be a little bit less robust, a little bit less accurate overall, so it's definitely preferable to use Bartlett's test when possible. In this case, we're probably far enough away from alpha to use Bartlett's test, but I'm just going to use both because it's easy, why not? And also then I can show you all the code for both tests, and you can choose for your own data which one you prefer to use. So I'm just going to open up a code chunk here. Now, Bartlett's test is in the stats package in base R, so you don't need to call a package for Bartlett's test. However, Levene's test is found in the package called car, just C-A-R, car. So I'm just going to use library. You can also use require to find car. You may need to install it first. And then we can just run both codes separately, both lines of code separately. So to do the Bartlett test, it's simply Bartlett with two T's at the end, not test. And then these tests, I like to give them the input in formula format, meaning y versus x, or response versus predictor. You can define it other ways, but I find this the most intuitive at least, and possibly the simpler, I'm not sure. And so we're going to define our response variable as chicks1 $weight, because that's what we're assuming is our response variable. And then you use a tilde. Now here again you can use spaces or you don't have to. I like the spaces so it's more readable. But you use a tilde to define that it's in formula format, and then you can give it your predictor variables. So chicks1 $feed. Then you need a comma. Actually, no, you don't. You don't need a comma. That is the end of that code. So we can run this first, because why not? Now, Bartlett's test of homogeneity of variances. It gives you the data that you're testing, gives you the k-squared value, which is part of Bartlett's output. I'm not exactly sure how you interpret k-squared, actually. And then the degrees of freedom is 1, and the p-value is 0.3624. That's quite a bit above our alpha of 0.05. We'll discuss what that means in just a moment. I'm going to run Levine's test now. Now this one is slightly different format, probably because it's in a different package, but it's just Levine with all E's test with a capital T. This dot test variant down here is deprecated, which means it no longer works. So we just use Levine test. There's no period in this one, and it has a capital T. But you give it the same exact input as you did for Bartlett's test, so we can just copy and paste that down there. And if we run Levine test, that gives you the degrees of freedom, which is also 1, this F value, and then this PR value is your P value. So this is 0.2533, which is also a little ways above alpha. Now, to interpret this, the null hypothesis of variance equivalence tests is that the variances are equal. So that's the null hypothesis. And with p-values that are significantly above alpha, we would accept the null hypothesis or fail to reject it, and therefore conclude that the variances are probably fairly equal in this data. So what that means is that between the normal tests being normal, or the data being normally distributed, and the equivalence of variance tests being also equal, we can use parametric statistics, which tend to be a little bit more robust to non-parametric statistics. And if those, assuming those assumptions are met, that the data is normal and variances are equal, we can be a little more confident with the parametric statistics being accurate in the way that they're intended. So, this is where we reach the point where our test choices diverge based on how many functional groups we're testing. What I mean by that is, remember that the original data had 6 different types of feed for the chicks. In this case, though, we're only testing 2. So I do have a sort of a cheat sheet that I'll provide probably in the next episode that lists 6 different tests that we can run based on the combination of the 3 variables. So that would be the number of functional groups, how many different treatments you're giving, whether or not the data is normally distributed, and whether the variances are equal or not. So based on the combination of those 3 things, you get 6 different possible outcomes. And in that, I have a list of tests that we can run based on those different outcomes. Actually, technically we'd get 9. I was just thinking about that, but in many cases, from what I was taught anyway, if your data is not normally distributed, then the variances being equal doesn't matter so much. I've heard differing opinions on that, so I won't get into that right now. I don't know enough to make a statement on it myself. But anyway, I have a cheat sheet, and basically, from what I know, based on normal data, 2 functional groups, and the homogeneity of variance, we can use the t-test here. So t-test is generally only used for 2 treatment levels, 2 different groups that you're comparing. And the code is very simple. It also comes from the stats package, so you don't need to call any packages. And it's just t.test. And we can give it the same exact input as we gave these guys with the formula, except we want to include an argument called var.equal, which tells it whether or not our variances are equivalent, because the alternative is that they aren't, and then it will slightly adjust the algorithm based on whether or not this is true or false. So we're going to say true because based on these tests it is equal. They are equal, so we're going to give it true. Now I think true is the default value, but I always find it's safer to just specify. Now if we run this, the t-test actually tells you the alternative hypothesis, which is that the true difference in means between group horsebean and group linseed is not equal to 0. So that means the null hypothesis would be that there is no difference in the means. It gives you the confidence interval. It gives you this t-value, the degrees of freedom being 20, and the p-value, in this case 0.008, is quite a bit below our alpha value, meaning that we can probably accept the alternative hypothesis in that there is a difference. It's not equal to 0. And it actually also gives you the means of the groups. So with that, we can say that there probably is a significant difference between these two groups. And that is really the end of the workflow. This is the result we'd be looking for in a very, very simple study, comparing these two groups. So the last thing really to do then is to visualize it. And in this case, several types of plots come to mind for this. For me, I think box plots or strip charts are a good way to visualize these things. I often like to combine the two, and I'll show you how to do that probably at the end of the next part of this statistical workflow, which is comparing all 6 feed types. But in this case, we can make a simple box plot using the box plot command. This is also built into base R, and it takes much the same form as the above code in that we can give it the formula. We want it to plot what's on the y versus what's on the x. And so this would be our weight or our response variable, and then our predictor variable being feed. Usually R is pretty good at dividing your predictor variable into different treatments if it's categorical. So in this case, if we look at chicks 1, our feed column is just horsebean or linseed. So generally, it should be able to break that down. Now, when I was testing this in my preparation for this episode, I came across a slight error, and you'll see what happens as soon as we run this code. You'll notice that it actually has all 6 feed types in this plot, even though our subset, which we're basing this code on, only shows the 2. This is all there is to it. It doesn't go any further up or down. It's all just horsebean and linseed. There's only 22 out of the total 71 observations. There's no indication that it has any other groups in it, and yet they still show up. And indeed, if I run the table command, which basically outputs a table of how many matches the function gets when it searches what you tell it to search for each individual different value. So if we do table chicks $1 feed, basically it's going to search through the feed column and come up with however many unique variables or however many unique values exist in it and tell you how many of each there are. If I run this, you'll notice it found 10 that are horsebean, 12 that are linseed, and it still lists these other ones, which I've never seen this happen before. I'm not exactly sure why it's happening. I ran some tests with different methods of subsetting the data. There are several ways to do it. I still find subset to be the best, and they didn't change anything by doing it differently. So I won't go through that right now, but I'm not sure why this is happening. It did not seem to affect the tests. You'll notice this 2-sample t-test ran these 2 samples, which are the ones we wanted it to run, and I don't think it would have run if it had been given multiple, like more than 2, because t-tests are designed for 2 different groups. So I don't think that it affected our statistics, but it is something to keep in mind as a potential source of error. There is a way we can fix the bar graph, not bar graph, the box plot. It's just slightly tedious if you have a lot of groups. With only two, it's manageable, but I'm really hoping this doesn't become a thing that I can't figure out, because that could become an issue. So let's look at a solution for this. To fix this, what we need to do is specifically manually say which groups we want it to plot. And to do that, we can take our predictor variable, the variable with the subtypes, these factor levels, and we can use, within the formula itself, we can use the factor command. So if we factor, we're basically telling it, hey, this is a factor, which is a type of object much like a numeric or a character, even though it's already telling it to change it to a factor just by default, because that's generally how box plots are made, so it's actually built in to coerce this to a factor. We can specify factor, and if we do this, then we are able to actually specify the order and inclusivity of the factor levels. So if we add an argument within this factor command after we specify the thing that we're factoring, we can use levels equals, and then we just concatenate the factors that we want it to include as a character vector. So we just need horsebean and linseed. That's all we need. So in here, we can specify with quotes horsebean, comma, linseed. Close that, and now we have our factored predictor variable. And you can also use this to reorder things. So if you wanted linseed to come first, like maybe you like it going from highest to lowest mean or something like that, you can also do it the other way around and just specify whichever order you want. But let's run this now, and you'll notice that we now only have the two, and it's in this order. So that at least provides a visual fix, if nothing else. I'm going to have to look more into the issue with the subsetting. I'm suspecting it might be a problem related to the match operator, but like I said, I've never seen this happen before. So it could also just be the data set itself, but I'll have to look into that. So anyway, we can clean this up a little bit more. I am going to do a whole separate video on making your graphs prettier in Base R, but this is kind of horrendous because it just gives you whatever you put into the formula as axis names. So we're going to bring this down to the next line with a comma here, and we can specify, just like we did above, I think, for the previous plots. If we look here, we specified the xlab for our histogram. We can do xlab and ylab for our labels. So xlab, in this case, it's also going to be feed, because it's our feed type. You could also say feed type, I suppose. And then our ylab is going to be the weight. In reality, it's probably actually mass, but same difference, in grams. And if we run that now, you'll see that that's changed, so it looks a little nicer. Just because it's quick, I'll include this as well. If you want to make it so that your y-axis tick labels here are not sideways, because I think this is kind of weird looking, personally, it's a very simple argument to add, just LAS. I forget what that actually stands for, but I think it's something about line adjustment or line alignment, something like that. And we can just say that equals 1. There are several different options depending on what you want to change. It's like different combinations of how you want to orient both axis tick labels. 1 means that they're all horizontal. So in this case, we can set it to 1, and these numbers should update to horizontal once I change that. And the other thing you might want is a main title with the main argument. So we could say chick weights, 2 feed types. You don't really need a title in most graphs, but if you wanted one, you could do that. And then you may also want to play with the colors of the boxes. To do that, you would just put the COL or call argument, And then you can concatenate a list of whichever colors you want in the order of your boxes. So maybe you want red and blue. Those are going to be very bright and vibrant, but they're really not going to have any meaning. If we run this, yeah, those are very bright colors. R has pretty much all of the common colors as well as hundreds of less common colors. There's a lot of very specific names for them. And I'll get more into the color system later on. I'm not too worried about it right now. You could also do like different shades of tan. There are, for most of the common colors, there's also 4 different levels of like dark versus bright. 4 is always darker than 1. So in this case, that changes it to light tan and dark tan. So you can play around with that as much as you like. That's just aesthetics. You'll notice our y-axis tick labels have changed here. So that looks nicer. We have this nice title. So that's a nice little box plot. In a future episode, I'll show you how to make a strip chart, and I'll also show you how to make them like together so that you actually put a strip chart on top of the box plot, which I like for various reasons, and I'll go into that when I show you how to make it. But with that, I'm going to call this episode done, and I hope this has been helpful. And the next couple episodes, I'm going to go through how to do the same kind of workflow, but with different tests based on using all 6 feed types as opposed to just 2, because the workflow will have to change slightly, at least after you test for normality and variances. Anyway, guys, thanks for watching. I'll see you next time.